To conduct the heat transfer through a composite wall. Aim to determine the overall heat transfer coefficient of composite wall. Here are the specifications of the experimental setup what we have. So this is a composite wall or composite rod. It consists of three materials: aluminium, material 1 aluminium, material 2 graphite, material 3 is cast iron here. Okay, the length of the aluminium rod, that is L1 equal to 100, L2 is equal to 20, that is the length of graphite. Length of the cast iron, that is L3 equal to 60 mm. The diameter of the composite rod is 50 mm. Then total length of the composite rod is 180 mm. Now this is our experimental setup what we have in our laboratory. First I will tell the parts of the name, parts of the experimental setup. First one, rotameter, temperature indicator, knob which is used to vary the voltage and current, power switch button, electrical heater, thermal insulation, water jacket and thermocouples. Okay, so now this is the main heart of the experimental setup here. So now here the composite rod is here inside and it is insulated by an insulating material. One end of the composite material is connected to electrical heater and one end of the composite material is connected to the water heater. This is the about experimental setup. Now how to conduct the experiment? First you have to switch on the power button, then you have to switch on the console, then you have to switch on the electrical heater, then you have to set the voltage and ampere by rotating this knob. After that you have to set the rotameter reading as you want, just as 1 LPM, 2 LPM, like that you have to set the rotameter reading. After that you have to leave the experiment for at least 20 to 30 minutes. Thereby 20 to 30 minutes. After that the composite material will get seated and it will attain the steady state. After the steady state you have to take the readings. After 30 minutes you have to take the reading. So what are the readings you have to take? I will explain. Okay, so now this is what schematic view of complete test setup. Now what are the readings we have to take then? How to take the readings? You can see here now. As I told you, 4 thermocouples are mounted on the surface of the test specimen. That test specimen is composite rod here. One is aluminium, graphite and cast iron. So two thermocouples you can see now. One end aluminum end and another aluminum end. It represents T1 and it represents T2. So and it is now here next it will becomes T2 and it is T3. Next it is T4. Okay, so now rotameter reading already you have set it as a 1 LPM. Is it right? You have set this rotameter reading by 1. So rotameter reading is 1 LPM. Okay, convert that LPM into kg per second. Now you have converted. Fine. What is the T1? You have to note down here now. How to note down the T1 temperature? By rotating this knob here now. By rotating this knob, you will get the temperature T1, T2, T3 up to T6. You can get it by rotating this knob. So same thing you have to note down your records. What is T1? 90, T2 82.6, T3 42.5, T4 40.8, T5 38.3 and T6 38.5, where T1 to T4 represents surface temperature of composite rod, whereas T5 and T6 represents water jacket temperature, where T5 is water inlet temperature, where T6 is water outlet temperature. So you have to take all the readings like this now. In what I have done, I have taken 4 readings. I have done the calculation. For calculation part, I will consider one reading, then I will do the specimen calculation. Okay, so now I will move towards calculation part. Okay, the first parameter is cross-sectional area of the rod. He has given diameter as a 50 mm, right? With help of this diameter, I can calculate the cross-sectional area. We have formula that is 5 by 4 into d square, right? Substitute and get the value cross-sectional area as A is equal to 0.01963 meters square. First parameter is over. Second parameter, mass flow rate of the cooling water. Where is the mass flow rate of the cooling water? So here you have set it, right? How you have set it? 1 LPM. 1 LPM you have set it. So then that 1 LPM you have to convert it into kg per second. Generally mass flow rate will be in kg per second. So 1 liter of water is equal to 1 kg of water. Then 1 divided by minute is there, convert it into second, that is 1 divided by 60, that will becomes 0.0166 kg per second. This is a mass flow rate of the cooling water. Second parameter is over. Next, third parameters, heat transfer rate. Heat transfer rate is nothing but what, when metal is gets heated, at that time what you will do, you will supply cold water into the water jacket, right? This cold water is going to interact with this hot metal, then it is going to absorb some heat and it will come out. It means water is going to carry some amount of heat. That how much amount of heat is carried by that water, that can be calculated with the help of an equation. What is that equation? QW is equal to MW into CPW into T6 minus T5, where T6 represents water outlet temperature, T5 represents water inlet temperature, and CPW represents specific heat of water, that is a constant. Already we know that 4.187 kilojoules kg Kelvin, whereas MW is the mass flow rate of water, that you already calculated. Now you know all the values, substitute in this equation, then calculate the heat carried by the water. That is equal to QW is equal to 0.014 kilowatt. Convert that kilowatt into 14 kilowatt. Convert that kilowatt into watt. You will get final answer as 14 watts is heat carried by the water. With the help of this heat carried by the water, we can calculate the thermal conductivity for the different material. I mean thermal conductivity for aluminum, graphite and cast iron. So first one, this is the base equation. You can see here now how I can write the thermal conductivity equation. K thermal conductivity for first material, aluminum. Thermal conductivity for aluminum is equal to heat carried by water divided by A into dt by dx. See here, first material, I will go here now. What I will do, I will simplify this equation now here. Dx, I will take it numerator side, whereas the equation becomes, whereas dx is nothing but for first material, change in length, right? Dx is nothing but what? Distance of the material 1. The length of the material 1 is nothing but what? L1. That I will write it here now. L1. So now it is a Q. Q I have written it as it is here now. Dx I have taken it as numerator side. That dx is nothing but what? For material 1. That is a L1. I have taken it at numerator side. Fine. Okay. Next A into dt is nothing but what? Change in temperature. Change in temperature is nothing but what? It is a 0.1 T1 minus T2 for aluminum material. Okay, T1 minus T2. Change in temperature is T1 minus T2. Now you return the equation in this fashion. Now you substitute the values. Q already you know here. L1 length of the material 1, that is aluminum, that is given in specification itself. Substitute here, that is 14 into 0.1 divided by A area into temperature T1 minus T2. As I told you, I will consider the last reading, right? I have considered the last reading T1 minus T2. Then I will get the thermal conductivity for the aluminum rod as 99.206 watt per meter Kelvin. This is first material. Similarly, go to the next material. So what is the equation? This is the same equation. Q into, whereas if you are doing it for second material, you have to consider L2. If you are considering second material, you have to take the second material temperature. How it is? Then Q into L2 divided by A into highest temperature T2 minus T3. The same thing I have written it here. Q into L2 minus L2 divided by A into T2 minus T3. Substitute and get the value. Thermal conductivity of graphite as 2.8 watt per meter Kelvin. Similarly, go with cast iron also. Now you got the, by doing this thing, you will get the thermal conductivity for aluminum, graphite and cast iron. After this, you have to calculate the overall heat transfer coefficient by practical. Okay, what is the formula for overall heat transfer coefficient? Here, U is equal to 1 divided by 1 by A into L1 by K1 plus L2 by K2 plus L3 by K3. So now here what you do, practically you have calculated K1, K2, K3. K1 is thermal conductivity of aluminum, thermal conductivity of graphite, thermal conductivity of cast iron. Substitute here now. So the same thing I will do here, 1 divided by 1 A is the constant for all. So A I have written here, already calculated. Next L1, length of material 1 is how much it is now? You can substitute here now. 0.1, then thermal conductivity is 99.09, substitute. L2 is equal to, what is the length here? Length of the material 2 is already you know, that is 20 mm, that is 0.02 meter divided by 2.8. Like that, third material L3, length of the material 3 is what? 60 mm, that is 0.06 meter divided by K3. K3 is nothing but what here? K3 is nothing but what? 102. Substitute and you will get the overall heat transfer coefficient practically as 115.02 watt per meter square degree Celsius. This is overall heat transfer coefficient by practically. Why it is practically? What we have calculated thermal conductivity by practically, right? The same value we have substituted here and calculated the overall heat transfer coefficient, then it becomes overall heat transfer coefficient practically. Similarly, same equation, what I will do? I will try to calculate the overall heat transfer coefficient by theoretical method. How it is? Same equation, but what I will do, instead of practical, what I will do, I will take the values, the thermal conductivity for aluminum, graphite and cast iron from the data handbook. These are available at the data handbook. I will take this value and I will substitute and I will get the overall heat transfer coefficient. That overall heat transfer coefficient is nothing but what? Theoretical overall heat transfer coefficient. Substitute here again 1 by A, area is same, length is the aluminum rod, that is 0.1 divided by thermal conductivity of aluminum rod from the data handbook is 204. Substitute thermal conductivity for graphite from the data handbook is 6. Substitute and get the values. You will get the value as 2. Now overall heat transfer coefficient theoretical is 202.78 watt per meter square. This is overall heat transfer coefficient. At the end you have to put the result. You have to write the result as theoretical overall heat transfer coefficient by theoretical approach is 202.7 watt per meter square. By practical approach is 115.02 watt per meter square. This is the procedure how to conduct and how to do the calculation.